Hello, everyone. Sorry. Good morning and welcome to this online event of GIMS Project, our project on the geodetic integrated monitoring system that was developed during this Horizon 2020 finance project. And welcome to everybody. Please send us your comments by writing on the chat during the whole event. We are here to present you how the project went, what did we do during this 3 and something more in 3 months duration of the project. And our main speakers will be Fernando Sansò, president of GReD, the leading company of this Horizon 2020 project, and president of GReD, and also professor at the Polytechnic University of Milan. And then we will have Mateja Jemec Auflič from GEOZS, the Institute of Slovenia, that participated and will explain how the deployment took place and what have been the main results. And finally, we will have our project officer, Joaquin Reyez Gonzales, who will give us an overview of the upcoming news on Horizon Europe for this specific sector. So I really ask you to comment and interact with us via the comment section on Facebook and YouTube. And we will be happy to answer during the event and after the event also. So I just call here with me Fernando Sansò.
So,
hello.
Hi, Elisabetta.
Good morning. Yes,
thank
sure.
you. Good morning, everyone, and welcome to this event. Let me remember that connecting to what our excellent speaker has already said, the GIMS project refers to Geodetic Integrated Monitoring System, which is designed purposely for monitoring landslides and risks on infrastructures. The project has been supported by the European Galileo Authority, and we had a kickoff November 17, 2017, and in November 5, 2019, we had a first meeting of this kind. It was not online because at the time, fortunately, we didn't have any COVID around. But of course, the first event was just to present the project and first results. Nowadays, we will try to go and explain what results have been achieved in the 3 years. And now just a short notice. Originally, the idea was that I should make the introduction, and then the principal investigator, Eugenio Realini, should make the first presentation on as an overview of the project. But unfortunately, Eugenio could not be here today with us because of some severe problems of health in his family. And therefore, I will have to make 2 presentations, which is, of course, boring for everybody. To some extent, you will see that there will be a certain overlapping between the 2 presentations. And of course, when you have 2 speakers, this is not too heavy. When you have 1 speaker, this becomes boring. But I will do my best not to be too boring. So I think we can start with the presentation, with the first presentation.
Thank you, Fernando. So I'll come back later. Now your presentation. Thanks.
Thanks. Okay. Nothing new in this first slide. As you can see, only there are the names of the participants to the consortium, but we will come back on that later on. So we can go to the second slide. So this is a general definition of the project: continuous geodetic monitoring of a landslide, studying its motion and the corresponding deformation effects on structures and infrastructures. We can go to the next. Now the targets will be explained somehow in more detail: to study the motion of the landslides and the possible deformation of structures situated in the area by integrating geodetic measurements performed with GNSS. We will use frequently this one, but especially it will mean GPS and Galileo, and SAR, the synthetic aperture radar technology, and IMU, the inertial technology. The integration between the three technologies is one of the targets. Second target is to design alarms, basically thresholds on movements and velocities. If you overtake the threshold, then there is an alarm, procuring the possible release of a part of the landslides of the or the crash down of structures. Third, next slide, the third target: to install a permanent monitoring system at a reasonable cost. Reasonable cost is an important, of course, reasonable is something value, but in this particular matter, it is an important concept because, of course, we are talking about risks and natural hazards and damages that can come to the population and to people. And of course, monitoring is an important and interesting target for the safety of the population. And if you can produce a monitoring at a lower cost, this means that you can monitor more. And this is important, of course. And provide solution time series plus alarm by a centralized analysis center. And fourth target: to make system operative and bring it to the market, cultivating relations with the final users. Next slide. I divided this talk in two parts: what we have learned, so the knowledge we have achieved, and the results that we have achieved. So what we have learned. First thing is that the target, the accuracy target that we had, 1 millimeter per day. One could think that 1 millimeter per day is too precise or not precise enough, but it is enough precise to monitor certainly landslides, and on the same time also to monitor structures, because the motion of structures is much lower than that of landslides typically. And the first thing that we have learned is that this accuracy of 1 millimeter per day in the position of a point can be achieved also with low-cost receivers, and that we could produce, well, design and produce a SAR active antenna of low cost with a millimeter accuracy along the line of sight of the antenna to the satellite. What we have also learned is that we could use tropospheric, the prediction of tropospheric, we can go to the next slide, the prediction of tropospheric corrections, which are particularly affecting SAR observations, and we can use them as derived from GNSS data processing to correct these effects on SAR observations. And this, as we shall see in the second talk, has an important effect. And then finally, that we have learned, well, originally we hoped that we could use IMU, even the inertial measurement, even to improve the accuracy on the estimation of the motion of points. But with low-cost receiver, we learned that this is not possible. Nevertheless, accelerometers and inclinometers can provide are excellent tools to provide alarms, sudden and pristine alarms for motions of the point. So next slide. Finally, we can comment that all in all, we have learned that very small signals can be detected by the integrated GIMS system, giving information and alarms in the form of a GIMS service to public-private companies interested in mitigating geological risks. Next slide. What we have achieved. From the point of view of hardware, first of all, we have achieved, so to say, the measurement unit, the boxes, panels, and so on. What I call the geodetic measuring unit, which collects data from a two-frequency, low-cost GNSS receiver, active SAR antenna, accelerometers, inclinometers, and transmit the data with proper rates to a remote data analysis center. Next slide. Again, what we have achieved in the software realm, we have a new GNSS software, operative, and including some which has been derived from an open source software that we have developed our own already years ago, which is called GoGPS, and in future it will be called GoGNSS, of course, to acknowledge the presence of all the other constellations. And this has a number of original features. The accuracy targets of the software are achieved processing low-cost receivers data. And I would even say I'm usually very attentive to not to exaggerate, but I could say that even we have better accuracy targets than one predicted. A low-cost SAR antenna and relevant calibration and validation procedure have been achieved from the hardware point of view, and an operative software for the processing of SAR. Next slide. An operative software, next slide, please, for the data from permanent scatters, and a pre-operative software. This means it's not industrialized as yet, but it works. We have applied it and it works for the integration of GNSS SAR tropospheric corrections. And a pre-operative software to treat data from accelerometers and inclinometers to issue the alarm. Next slide. So again, what we have achieved, because this is a result, the experience of more than 1 year, in fact, of integrated data analysis and GIMS service, end-to-end service, for 2 case studies on which we will return, Vipava and Potočka, 2 sites in Slovenia where we have studied the relative landslides. Okay, next slide. This means that the first talk is finished, and we can go now. I leave out my hat of Fernando Sansò, and I have to put on the hat of Eugenio Realini. And so I will talk about a presentation that he prepared, but I will present. So next slide, please. The first slide of the second talk. Okay, perfect. I think we already commented on that, and we can go to the next slide. This is an illustration of the consortium that has been working on GIMS. As you can see, it's GReD that somehow I represent. which is a spin-off of Polytechnic of Milan, and has been the coordinator of the consortium and in charge of GNSS data processing, as well as the project management. The next company in the consortium was Safirian, which is a GNSS hardware company from Switzerland, and they were in charge of design and development of the geodetic measuring unit. So not only of the development of the GNSS, but also the unit that collects data from GNSS and all the other sensors and transmit them. Geonumerics, which is a company in Catalonia, which was in charge of the processing of IMU data, inertial data, and then CTTC, a research center of the University of Catalonia that was in charge of the development and of the active SAR antenna and of the processes of all SAR data. ComoNExT itself, which is a hub here in Italy, close to Como, and that was in charge of communication and dissemination and business development. And finally, the Geological Survey of Slovenia, that was in charge, first of all, of the choice of the sites where to make the demonstration of the system and of the validation of the results. Next slide, please. So let's comment again on the key factors of the GIMS project. First of all, it's a low-cost solution designed as an end-to-end service. So we had to design a service showing that it was working, from data on the field and to data released to the end user. The integration between GNSS and INSAR stands for interferometric SAR, from the satellite Sentinel, so the satellite constellation of Sentinel, and the IMU, the inertial unit. This gives point-wise high temporal resolution at certain points where the GMU are deployed, but also at the same time with a much spatial resolution and a much larger number of data in the area from the INSAR. And it is the combination between these two things, very precise information at points, let's say every 15 seconds, at points where you have the GMUs, and once every, let's say every week, 5 days or so, information on all the permanent scatters that reflect the, as well as the active antenna, SAR antenna, that reflect the interferometric SAR data. Now, targeting different ground movements, this is exactly what I just said: point-wise low deformation, area-wise deformation. Rotation and accelerations are connected, of course, to the alarm. Accelerometers can measure accelerations, and they can give you, if a certain point starts moving suddenly out of what is predicted from a stationary movement, and therefore to launch and to issue an alarm. Next slide. We have to underline, of course, I mean, we are working, let's say, somehow on behalf of the Galileo Authority, and so we have to say something specifically about Galileo. So what is the role of Galileo? Why is Galileo Authority interested in such matters? And the result is, from the project, is very clear. And this is that the monitoring dual monitoring with GPS and Galileo, and possibly also in future with other constellations, but especially these two, make much more reliable the monitoring. Because we know GPS can be very precise, even with low-cost receivers, but it has the bad habit sometimes not to work properly and so forth. And if you have two systems on the same time, you can rely on one when the other is not working. So you don't have gaps in your data and in your data analysis. And with the second frequency for civilian usage on all the satellites of Galileo, this is giving quite independent and improved solutions. Improved, why? Because the combination between the two constellations, of course, improves the accuracy. But we have proved that even if we use Galileo data only, the solution is there and it is usable. Now, next slide, please. Now, something lighter. You can see the GMU deployed. And here it is deployed on a pole. There are various kinds of monumentations, and here you have all the instruments. The electronic is in a box, but of course the antenna is on top of the pole, and we have the active antenna, you may think that it is a secondary element of only technical value, the panel, but I can tell you that the panel is extremely important, because you have to have the right panel to produce alimentation for the GMU, including alimentation to transmit the to help the active antenna when it has to work, because of course it works once a week maybe, but when it has to work, it has to be alimentated. And the panel is a critical thing, because electricity has to be there when you have to transmit, otherwise transmission is not working. And especially when you are in the mountains, as you will see in a minute, the panel can be covered by snow, for instance, and at that time it is not working properly. So you must also have an archiving system in situ in order to get the data and send them when the transmission is and the connection is again reactivated. You can go to the next slide. And this one you can skip because it's practically the same thing. And you go to the next one. And here you see the two sites, a small map of the two sites where we had landslides to monitor. One is called Vipava, and it is on the left, and the other one is on Potoska Planina. And the two landslides are different in nature, because in the Vipava sites, you have slides with very slow movements, but they are dangerous for a highway that you see there. And if any movements, the landslides can stay still for 1 year or so. On the contrary, on the Potoska Planina, the landslide is moving much faster, centimeters up to 10 centimeters per year. And what is important is that the area of Potoska has already been studied by several other actions in the past years of the Geological Slovenian Service. And so we can compare data and validate the results that we got there. Next slide, please. Here you see again a view of the Vipava area and the spatial relation, so to say, of the landslides that hinder the highway. So 3 locations have been selected on the highway, and next slide, 7 GMUs have been deployed, and of course one of the GMUs has been deployed, which is called, for some reason that I will never understand, VPAVA 7. But this VPAVA 7 is, as a matter of fact, the reference station for the whole movement in the area. As you know, the whole data have been processed in a relative mode, because processing GNSS in a relative mode gives a higher accuracy, and we wanted to reach, as I said, the millimeter per day accuracy, which was possible exactly because we had this relative mode way of considering the data and analyzing data. In this respect, it is important to also to underline that, of course, even when we say that we in precise point positioning, for instance, we make an absolute assessment of the movement. This absolute assessment means only that you have a much more remote reference system. But of course, this is of less interest in a sense, because it's less accurate. And on the same time, what you would like to know is the local deformation of things. And that's why having a reference station is always useful and important, as well as important is the choice of the point where to put the reference station, because it has not to be affected by the same phenomenon that produces the landslides. Okay, we can go to the next. Here you see some particular and different monumentations. Some of them are directly on bridges of the highway, and some of them are on platforms. But what is important is that monumentation, again, can seem to be a secondary argument. But when you have to see millimeters, you have to be sure that your station is monumented in a way, is clamped to points which move with the structure that you want to control. Otherwise, of course, you can only describe the movement of your station, which might be different from the movement of the object that you want to control. Next slide. Then you see here the area of the Potocka Planina. As you can see, is a much wilder area. However, the landslide there, if I understand it correctly, can hinder some buildings, and it is important to monitor these landslides. Also because, as you can see in the next slide, you can see that the terrain there is not so regular, and so it was even difficult to make monumentations. But fortunately, we could take advantage of some strongholds that have already been established, as I said before, by previous projects. And this was important because returning to the same points, we could have comparisons with other data. Okay, we can go to the next slide. What we see here, and in the next slide, are some examples of what is an alarm. Here is for accelerometers, and the alarm simply is a specific algorithm that, even though you have a large noise on your data, by adding and accumulating your data, you're able in a short time to give an alarm for a motion which is irregular, because the accumulation of alarm is, so to say, stronger than the accumulation of the noise. And in the next slide, you see another typical effect that we had to take into account, which is an effect on clinometers. And clinometers have this bad habit of having trends which have nothing to do with rotations of the platform on which they are placed, but they are just instrumental trends. So what you can see here is that if you go to the red curve below, you can see clearly that at a certain moment you have trends, and these trends have nothing to do with rotations of the structure, which is important. Otherwise, in our case, that would mean that we had to go on, because you imagine you just monument a point on a landslide which is moving, really moving, and then of course this platform could rotate. So it was important to distinguish whether we had a rotation of the platform or a shift of the base of the platform, which means the real motion of the landslide. But as you can see, if you take into account the correlation of this inclination data with temperature, then you go to the blue curves, and as you can see, you can correct for effects which are purely instrumental effects. Now we go to results here, and then we go to the next slide. Here, an important achievement that we could get in, it is a plus of merging data from GNSS into with the SAR data, with the radar data, and this has to do again with another effect which is typical of SAR data, namely the SAR data. I mean, in order to transform your data into movements, you have to suppose that high frequency data somehow are not related to the movement. And so you detect your movement by making a linear adjustment of your data, and you detect a trend. And now you have to decide whether this trend is a trend that has to do with motion or with some other phenomena which are of several nature, but they might be due also to effects of topography on the waves that come from the satellite to the transponders, to the scatterers. And in fact, this is what we were able to prove, because since the GNSS sensors are able to distinguish between the correction of the troposphere, humidity, basically in the atmosphere, from the motion, something that SAR is not able to do alone. So if you try to, if you look at the left plot, you can see that the trend which is detected by SAR is the red curve, is the red line, the straight red line, while the trend and the slow motion detected by GNSS is the blue line, in practice no motion. And the two things seems to diverge significantly. But if we correct the tropospheric errors on the SAR data, and then we treat the SAR data with tropospheric errors corrected, then also the SAR data give you something which is very much agreeing with what we have concluded with what we have concluded to from GNSS. So the two techniques are agreeing one with the other, and if you make the integration, and this means that you can use also all the permanent scatters that are spread all over the area, not just the 7 receiver in Vipava, but all these permanent scatters to get more information on the motion of the landslide. Finally, next slide. Here is something about the business development. I'm not particularly expert, but one thing I want to call your attention, we have two slides on the right here, showing the risk of landslides connected to the seismic risk on the left, and to the right, connected to the precipitation. And of course, as you can see, well, Italy is always under risk, because Italy is, so to say, the paradise of geologists that want to study risks. But also other areas in Europe, of course, are prone to risks of this type. And therefore, there is the possibility of getting, let's say, an important potential market, not only in Italy, but also in other areas in Europe. Next slide, please. So summarizing, and I come to the end. We had 2 test sites and a service that has been based on 14 stations of GMU that were deployed on the 2 sites, and that have been working by something like 1.5 years. Working means that we have processed data and delivered data to the Geological Service. We had the SAR data as well that have been deployed, in fact, on 2 sites, and we have achieved the open source engine of the software that, as I said, is open source as we promised, and the SARS processing software, and innovative algorithm to integrate the GNSS and SAR data to issue timely alarms in case of fast and sudden motions. So next slide, and this is the end of my talk. I think I'm perfectly in time, and the next slide shows thanks for your attention, and this is the end of my second talk. I think
thank you, Fernando. Here I am. So thank you for this overview of the project. As ComoNExT, we worked together with the consortium in particular to the, let's say, last slides that Fernando was showing. So about the business modeling and business plan. So what could be GIMS future on the market, and what we could really understand from the market analysis is that the European market is, of course, the most relevant for the partners involved, and also because of course, the technology is developed in Europe, but as it was mentioned a few times during the presentation made by Fernando, what is interesting is that this is a low-cost solution, meaning that the quality is ensured, but the final price will be much lower than what is now on the market. And this is one of the strengths that, let's say, GIMS partners aimed at the beginning of the project, and were hoping during the proposal phase, and that was confirmed at the end of the project. So I just wanted to, since we had this role within the project, that I just wanted to underline that. So thank you, Fernando. Now we will go to the next presentation. by Mateja Jemec Auflič, that is a project coordinator on behalf of the Geological Survey of Slovenia, and she will give us the perspective of the end user. I mean, they really monitored and managed all the deployment work. So I give the floor to you, Mateja, and see you later.
Okay, thank you, Elisabetta, and good morning to everyone. I will present the GIMS results from the end user perspective. So the main role of our Geological Survey of Slovenia and GIMS project was to select the pilot area for GIMS deployment and validation of the monitored data. In the next 20 minutes, I will take you to the journey from the beginning to the point of installation of these two nice units that provide the real-time monitoring data of landslide activity. When we talk about the landslide, the first logical question is, what is the landslide risk for a community that lives in the vicinity of a landslide? Therefore, one of the first activities to answer this very important question is definitely to monitor landslides. However, understanding the landslide dynamics is necessary to reduce the landslide hazard and to develop appropriate mitigation measures. And on the basis of the landslide monitoring, the early warning system can be established. Moreover, the early warning system has proven beneficial in the process of understanding and evaluating the effectiveness of mitigation measures. In the last 20 years, we have witnessed events that happened almost suddenly, unforeseen. Several catastrophic landslide events hit the communities in Slovenia and endangered human lives and infrastructures. Unfortunately, 7 people also died. And due to diverse geological and tectonic structures, landslides occur very frequently. This is a map of about 2,000 recorded landslide events in the past 15 years. Many of them are not mapped in the map due to the incomplete information. So this map clearly evident that the landslide observation is a very important task of the institutions dealing with hazard. So in GIMS, we focus on the advanced low-cost monitoring system based on GNSS, Copernicus R, and inertial measurement units. However, landslide can be monitored also by geotechnics, geophysics, hydrological techniques, and also mapping. Which technique is used depends mostly on what type of landslide we would like to monitor and what kind of expected velocity we expected. Important is also temporal resolution. Of all the landslide monitoring techniques, geodetic measurements usually provide the highest accuracy, in some cases even sub-millimeter levels of accuracy. The results of geodetic measurements are precise, absolute 3D coordinates of points on the surface, as well as absolute changes in position. These measurements provide an invaluable framework for landslide motion monitoring. Having this in mind, we had to also check the equipment specification and requirements to obtain qualitative monitoring data before the final selection of pilot area. So for GNSS, it was very good that we have open sky visibility due to the GNSS antenna. Slope-oriented, it's very good that slope is oriented toward the south directions. Then very required is also reliable 3G connectivity and as much as possible safe places. For the SAR, it is very good that sliding slope is oriented toward the east-west direction, that the landslide body includes rocks, rock outcrops, buildings, infrastructure. This is due to the SAR procedure and for the detection permanent scatter points. And again, also is very important that, let's say, that the place, that the landslide, that the location is as much as possible safe. For the inertial measurement units, as Fernando say, we would like to have landslides with a sudden movements. Given the equipment requirements for the optimal units function, we have selected two study sites. The first one is in the Vipava Valley, southwestern part of our country, and the second one, Potoška Planina landslide, in the northwestern part of country. Both pilots are characterized by landslide activity and present hazards to the community and infrastructure in the case of failure. The specification of both landslides are different, and I will talk this in the few next slides. So let's move firstly on the pilot area 1. This is in the Vipava River Valley. Here we have a complex recent landslide that are related to the carbonates that are thrusted over folded and tectonically fractured flesh. The combination of unfavorable geological conditions and periods of intense short or prolonged rainfall has led to formation of different types of complex landslide. And across this valley, we have a 10-kilometer motorway is crossing here in this part, and this road represents an important connection between central Slovenia and northern Italy. Actually, this route was chosen to minimize landslide areas, let's say, to stop sliding, and to retain water source for the villages in the Vipava River Valley. The construction of this section started 2003 and was finished in 2009. During the construction, some landslide activation occurred, and to minimize the sliding movements, many retaining walls, structures, shafts have been carried out. But sliding actually minimized, but it is, as we observe from the monitoring, this area is still active. To find the best monitoring point, we carefully check the potential of the most sliding parts of the high road. We focus on viaducts, bridge, retaining wall, concrete shafts, actually where we could expect the higher displacement rates to be monitored by GIMS. Actually, when we're looking for the best place, we consider the fact that you need not hamper the traffic, road maintaining, and that the place is relatively safe from the possible tips. Also, colleagues from GReD joined us to check the installation feasibility of selected points. So altogether, 7 units, including reference points, was integrated and installed along this road in these 3 locations. The first one, the second one, and the third one. So just a little bit about the installation. The installation was taken in June 2019. The team consists of technical experts for the installation. These experts have done similar work before, as Fernando said. So for that reason, it was possible to perform really good job. IT experts also join us, and also geological experts. Not even a photograph was missing. Due to the strong wind, we produce a little bit stronger load structure to which we attach the GIMS units. And here you can see just a few snapshots from the field work. So the core of unit is boxed with a battery and microchips where the GNSS data are recorded and transferred then to the FTP server for further processing and calculation of the displacement. The other important components are also GNSS antenna, very important solar panel, inclinometer, of course, we also attach to this unit, and active corner reflector. And even the track of spaghetti was not missing either here. In parallel, the group from CTCC Barcelona, this was experts for the SAR, prepared the active corner for the installation. While the GNSS components were transported by the technicians from Italy, the components for the active corner reflector were transported in big box by the plane to our institution, and then we pick up this box and transfer to the pilot area. As you can see, again, very precise work was needed and 2 active corner reflectors have been installed. Here, now you will see the short video about the installation. Okay, so now let's see the very important part of these GIMS units. These are results. So after the successful installation, the first results were obtained at the end of June last year. We observed the period in Vipava Valley from the June last year to the end of, in the June from 2019 to October last year. So 1 year and 4 months long period. As you can see in this figure, the dispersion of the data are very high for all GIMS units practically. Why? This could be due to the heavy traffic on the motorway that results in constant vibrations. And the GIMS units detected no considerable displacements of monitor sites during the observation period. Actually, some increase monitor displacement trend was noticed only at unit 2, where this is on the viaduct on Shumjak, and this site was measured, and we it's presumed that is a little bit more active than other two pilot sites. We could conclude from these results that there are not such a big movements, but the movements are rather slow. It is also true that no extensive rainfall occurred during the observation period. So now let's look the results from the SAR. In the wider area, one active corner reflector actually detected several displacements, siding up to 3 centimeters per year. These detected displacements are related to the different concrete structures as well. SAR technique does detect the displacement that are actually seasonal oscillation of the material. Actually, the validation with the data from geotechnical monitoring was not possible entirely due to the unavailable data. Okay, let's see the situation on the Potočka Planina landslide on our second pilot area. Actually, this Potočka Planina landslide is situated above the village with more than 2,000 inhabitants. And already and recently, this landslide was investigated with many geotechnical boreholes and other geotechnic techniques to investigate and to identify the movement rates and the depth of the sliding surface. In the upper part of the landslide, we have a scree deposits. This is in this part. You can see the picture here. This is in the upper part of the landslide. In the middle part of landslide, we have fresh, very fresh open cracks, extensive cracks, and very hummocky terrain with many curved trees. Upper part is presumed to be the most active part here, where all material from the landslide accumulated. And due to the water stream, it is high potential that this accumulated material could mobilize into the debris flow and endanger the village below. So here, altogether, 7 GIMS units were installed. The installation were performed in October last year, in October 2019, with a similar group of experts like in the pilot one. And due to the mountain climate and winter snow, the steel structure has to be above 2 meters high for the reason that GNSS antenna is not covered by the snow. The GIMS units were more or less installed on the rock outcrops. And one thing, the location of units are remote from the road, so the installation required walking and carrying material over these pine bushes steeply upwards. Okay, let's look the results. As I mentioned, as a total 7 GIMS units were installed in this site. The first 3 GIMS GNSS units were integrated here in the upper part of the landslide to monitor the activity of the scree accumulation zone of the landslide under the steep slopes of the Rocky Mountain Ridge and define landslide chrome. Here are the results of these 3 points. You can see 1, 2, 3. These are these points that indicate on continuously displacement rate in this upper part. You can see the sliding from the observation period from October 2019 to the October last year. Then 2 points, 2 GNSS points were integrated, installed at the let's say to observe the secondary landslide boundary and to test the activity of the landslide here in this part 4 and the position of 6. Here you can see the results, the yellow and the green curve, and show that very small displacements were detected during the 1 year of observation. Then another GNSS unit was integrated on the big boulder here in the most active part of the landslide. This unit is number 5, and you can see a really big displacement shifts during the 1 year of observation. And Unit 7 present the, let's say, the geological stable area, and we represent this for these units, for this unit for the reference point. So good spatial coverage and high precision of the measurements obtained with GIMS units enable understand this complex kinematics of the landslide body. So as from the results, we could say that the upper part moves at a rather constant rate, and it's only minorly influenced by the rainfall, while the southern flank is rather stable and active, while this part is most active, what was also measured by the GNSS GIMS unit. What these results mean in comparison with other geodetic measurements we perform in the parallelly, not inside of the GIMS project, but other project, you could see that the obtained results are very similar, and that both techniques, GNSS and other geodetic measurements, show on a very similar displacement rates and at the similar position. So from this point, we could say that the GIMS unit show and reflect very comparable results with the other geodetic measurements. Based on this knowledge and results of 1 year-long monitoring of Potočka Planina, it was possible to estimate also the yearly surface displacement rates of the landslide. So such outcomes supplement the deep displacement data with the data on surface displacements. These data give also insight into the spatially complete landslide behavior that will help establish displacement rates needed for risk mitigation. Extended monitoring period will allow building correlation between landslide behavior and precipitation and help to determine displacement threshold values as prediction landslide future movements. So I have come to the end, and from the end user perspective, we could see that the needs of the implementation of GIMS and user experience enables developers and even management to understand how an application's users are faring. First and foremost, this data is critical for discovering how successful GIMS units are in servicing its customers. In this view, my conclusions are, and our experience are, that the small and compact GIMS units are relatively easy to install in even remote and inaccessible areas. And then the GIMS units provide data with good spatial resolution and enable good insight into the landslide body. And continuous measurements with data acquisition enable near real-time monitoring. And at the end, the validation proved that the quality of measurements of the GNSS segments is comparable to other relevant measure techniques. So this is all for now. Thank you very much for your attention.
Thank you, Mateja. This was very, very important, a very, very important result, and also to have an end user on board of this project has meant a lot, because we can really, let's say, prove what were the initial insights. And as Mateja said, having a very easy to use and to install solution, but also with a very competitive price and important results. I mean, I think one of the strengths of this project, I mean, we mentioned before the lower price compared to other other solutions on the market is one of the strengths, but another one is the integration. And actually, one of the aims of the project was to, let's say, integrate the results coming from different technologies within a very simple report to read. So one of the ambitions is also that let's say other institutions or civil protection units, municipalities and regions, specialized agencies within European regions can really look at this solution as a new standard for the monitoring system. So this was the ambition. I think this is still the ambition of GIMS project. And thanks to the Geological Survey of Slovenia, we could prove that this is a very competitive solution that is now on the market, that is available on the market. And it can be really a game changer within the monitoring of landslides and structures market. So thanks, Mateja, very much for your intervention. And I give the floor now to Joaquin Reyez Gonzales. Now we want to look at the European perspective to the future. So with an outlook to the Horizon Europe framework program for innovation. And yes, Joaquin is a Market and Development Technology Officer at the European GNSS Agency. And it was, of course, our reference point within the agency during the development and implementation of GIMS project. So welcome, and I give you the floor.
Okay, thanks a lot, Elisabetta, for your kind words. It's always a pleasure to be here in a final meeting when everything worked and when you did such a great job. I have to start just saying thanks thanks for doing your best, and thanks for being able to achieve all these wonderful results. Is clear that I mean, in the corner on the left, you see the number of companies that were supporting here. So I have to congratulate all of you. I mean, not only the ones who are present here and the ones who are presenting. Is just to congratulate all of you to achieve all the results. I am still saying that okay, my favorite meeting is the kickoff meeting, because in the kickoff meeting you can see your. I mean, I am usually able to see your smile and your enthusiasm and how you see. And in the final meeting, I see I mean, how you are reflecting, how proud you are about the work, but always thinking about the future, and always with this dab in your face. And this is a good point. I mean, I have to admit that this is research and development. We are trying to do something that nobody else did before. So we need to really appreciate the things that we have done. And of course, as you were saying, now is time to think about what is coming next. I mean, so what is in the future. So I am not delaying anymore my presentation. So I will go very quickly to what is happening from the European Commission and from the European GNSS Agency in relation with the funding programs. So I think that today, after 3 years, you already know that GSA is headquartered in Prague. In this difficult situation, we are all at home. I am at Prague. In this particular case, we are used to use connection, and we are used to do the video conference, because GSA has several premises around Europe. So it's not only the headquarters that we have located in Prague. We have premises around whole Europe, and this is really a way to succeed and a way to have redundancy. Then the next point is the evolution. I mean, I think that it's clear that future is the key word of this presentation, what is coming. So GSA is growing. I mean, meaning that we will do more things than the ones that we are doing now. And it's evolving to what we will call a EUSPA, or European Union Space Program Agency. This is the new name, but with the same people or even more people working with us. So basically until 1st of January 2021, so basically until 20 days ago, we were only working on Galileo and EGNOS, and now we are also working in Copernicus, GovSatcom, and Space Situational Awareness, meaning that we will be able to work with another more than 125 European satellites. So it means that what we are doing is somehow good for everybody, and we are receiving a good feedback, and we are growing. And I have to admit that we cannot grow without you and without this kind of projects. So again, thanks, congratulations, and let's move forward. Okay, the next point is how we see GSA and how we are thinking about how EUSPA can evolve. So we are typically saying that we have 3 pillars. So they are basically market and user knowledge, when we are analyzing the situation, and when we are, let's say, trying to understand how the users are using the services. And we are also transmitting to all the users this information. So we are like acting as a hub of information. Then we are giving support to European Commission and to any public entity who is requesting this support. And the third pillar is basically the reason why I'm here, is funding opportunities, Horizon 2020, fundamental elements, grants, and all the contents and prices that we have also on the left. So it's not only this project, but this is a clear example about all the things that we have done, how we are able to work with you, because I do like to say that we are working with you, close to you, in order to develop something that in this case is really, really something innovative and nobody else did before, as I said. So this is the reason. However, the situation is evolving, and Horizon 2020 has no sense in 2021. So now we are calling Horizon Europe. So we are basically taking the lesson learned of the previous calls. I know that GIMS is from the call number 3. We have up to 5 calls in Horizon 2020, and now we are thinking about how we can use all these lesson learned that we took from the previous projects and going further. So be sure that we are listening to you and we are understanding your issues, and we are trying to improve, and we are trying to take on board all this information in order to continue working with you. So then, I mean, what is the challenges that we have? I mean, first is taking the feedback, is analyzing what we have done good, what we have gone not so good, and then trying to improve. But it's clear that we have, all of us, we have now these 12 objectives in our heart and in your heart. So we need to make a better world. Basically, this is the summary of this slide, and we cannot do it alone. I mean, we need you. We need all of you, and we need to let's say go this one step ahead, and trying to improve what we are living or what we are the world that we are living, and to our family and to our children and to the next generations. So we need to improve all the things that we are doing, and we have to be more sustainable and having just a better life. Okay, so how we can do this? I mean, of course, first slide about the future has to provide a clear message. I mean, all of us, we are Europe, and we need to defend the Europe brand and the Europe flag. So I think that in this situation is when you really realize and assess what is the important here, and how, if you are together, you can go further. And this is also the message. We need to work for Europe, and we need to work as a team, all of us. And I think that this is, again, this project is a clear example about several companies from different countries working on the same direction. So in this particular case, the magic number is 100 billion of euros. That looks like is a lot, but when you are trying to say, okay, how this amount is split, or how this amount is organized, I can say that if we want to continue with this line, that where we are in digital industry and space, this is the part that we have. So basically, these 100 millions, they will be used for several purposes, and we need to focus on the ones that we call global challenges and European industry cooperation. So this is what, or competitiveness. This is what we are working all together. But don't forget all the topics and all the brands that we are using, and all the branches that we are working on. Okay, so this is basically the last point, and I think that the idea is, I will invite you to share and to look for the concrete details. But considering the amount and the budget that I was presenting before, the idea that I was also presenting before, that we need to improve the quality of life, the world that we live, and everything, Now, what are we completely looking for? I think that in your case, you clearly know because you success in the proposal. But I am also I am also thinking about the ones that may be listening to us and saying, okay, I love this GIMS project. It's a very good one. I want to work in this direction. I want to do something similar. Okay, my invitation, the door is open, and my invitation will be focused on, okay, you need to be ready, and you need to prepare a good proposal, and you need to focus on basically 3 different branches and 3 different pillars. Again, I do like the number 3, and I think that is everything you can basically split and organize in 3 branches. And in this particular case, we are also looking for something that has to have a scientific impact. So as we were being able to listen from the members of the consortium, you really do something that scientifically has a huge impact, and is something that is really helping to the people and to the universities and scientific community. Then, of course, we need to provide also impact at the social level. So not only for the people who are working on this field, you need to provide impact. Also for the ones that doesn't know. In the case of GIMS, the people living in the areas where you have this activity, seismic activity, they will realize what is the advantage, because they will be able to monitorize everything. And last but not least, of course, economic. I mean, I am talking about budget. It's clear that everything is somehow related with the economic part, but you need to also provide and develop European industry. I have to insist in this European flag idea, and we need to develop the companies, and we need to develop the industry in Europe. So this is basically what I wanted to say. Of course, I will stay here for listening any kind of questions, and I think that Elisabetta will provide more details. But I am sure that this event is recorded, will be available. Questions may be done also offline, so don't hesitate. Thanks a lot. Congratulations. And please, let's continue working together. Thanks.
Thank you, Joaquin. Really, I just want to connect to your presentation, because I believe one of the great impacts of GIMS project is at the social level. I mean, we had always in mind, while implementing the activities, that population was one of the main targets, like the protection of population. That's why we have tried to contact with civil protection and other institutions, just to show that this could be, like, including accelerometers, inclinometers, was aimed at really giving an instant warning for, let's say, avoiding the impact of natural disasters on the population. So this was for sure one of the main objectives of the project, just to underline how this European project involve impact and are aimed at, let's say, improving the situation of the population and of European citizens as well. So thank you very much. And
also, I mean, scientific community, economic impact. I mean, you did everything. I mean, I cannot really complain. Really lucky to have this kind of projects, because really is when it's really easy to work with you, it's really a pleasure. So someone is saying that once you love what you do, you are not working anymore. So you are making this one easier. So thanks a lot.
Thank you, Joaquin. It's been a pleasure to work with you. And so I invite our participants to leave their comments, and we we give a last hi to everybody. Thanks for being here with us. And of course, the comment section is open. Might you have any questions? And the GIMS website will stay online. This event is recorded, so you will find it at the links that you had initially on YouTube and Facebook. And on my behalf, I greet you all and thanks for the great work. And we are here to answer your question now, later. And thanks a lot for being with us. If you want to say just a word for, bye-bye.
Bye-bye.
Thank you. Thank you very much.
Okay.